Hello friends, I hope you all are fine. So today's topic is from the control system and the name of the topic is steady state error calculation. Okay, so the notation for the steady state error is E steady state, and yeah, it is very easy concept, and yeah, let's see what are all the concepts related to the steady state error calculation. So, as you all know, uh, if the actual output of a control system during the steady state deviates from the reference input, that is desired output, the system is said to possess a steady state error. And yeah, these errors arises from the nature of inputs, the type of the system, and from the non-linearity of the system component, such as the static friction, backlash, etc. And yeah, aging or deterioration, these are also the factor which cause error. Okay, so over here our error signal is nothing but the difference of reference signal and the feedback signal. Over here you can see from the block diagram itself, like the error signal is nothing but the difference of the reference signal and the feedback signal. Okay, so yeah, here is a slight modification. Here E of t is R of t minus C of t into H of t. Okay, I'll explain this in detail just a minute. Okay, yeah, so let's assume here is the b, which is equals to c of t into h of t. So b is equals to c of t into h of t, and the error signal is r of t minus b. So this entire quantity is nothing but the b. So e of t equals to r of t minus c of t into h of t. So the formula of steady state error says it is equals to limit t tending to infinite e of t. At infinite time, we are just calculating the error, and this error is known as the steady state error. Yeah, so by using the final value theorem of the Laplace transform, steady state equals to limit s tending to 0, s into e of s. So this time domain is converted into the s domain. Okay, yeah. So here is the analysis for the entire steady state error calculation. So here is our R of s, here is the error signal, here is the output, here is the feedback path, and it is given to as a unity negative feedback. Okay, so here I am assuming it is B. So B is nothing but B is equals to H of s into C of s over here. So E is nothing but R of s minus B. So over here E is equals to R of s minus C of s into H of s. This is the important result. Okay, yeah, so this result only we are going to see, and you consider this block diagram the transfer function which we can obtain, which is equals to output by input, which is equals to g of s divided by 1 plus g of s into h of s. This is the negative unity feedback transfer function. Okay, I think this is very basic and you all know that. Yeah, so here is E of s equals to R of s minus C of s into H of s. When you divide it with R of s, so E of s divided by R of s equals to 1 minus C of s into H of s divided by R of s. Over here you observe this C of s divided by R of s is nothing but our transfer function. So when you substitute this entire value over here, you'll get E of s divided by R of s, which is equals to 1 plus g of s into h of s minus g of s into h of s. So these two will get cancelled. So ultimately we are getting it as an E of s divided by R of s equals to 1 plus 1 divided by 1 plus g of s into h of s. Okay, so when you substitute this value over here, limit steady state error is equals to limit s tending to 0 s into E of s. This E of s over here you can just substitute from over here. So E of s is nothing but R of s into 1 divided by 1 plus g of s into h of s. So this is the ultimate formula which you get over here, and this is the important result. Okay, yeah, so let's discuss the another important point, which is in case of non-unity feedback system, for example this our h of s not equals to 1. In that case we have to make the system a unity feedback system, and then we have to use this particular formula for the calculation of steady state error. So in case of non-unity feedback system, we have to first convert it into the unity feedback system by just adding the block -1, and over here we have the +1. So this is nothing but this particular outer feedback loop is nothing but the unity feedback, and when you club these two particular uh, blocks, so they will become the one block, which is equals to h minus 1, and this entire thing will become the one block. So this entire transfer function, entire block is just converted into this particular block over here. So here is our R of s, and g divided by 1 plus g of h minus 1, like this is the feedback loop over here. So this is C of s, and this block is nothing but our unity feedback system. Okay, so in this manner you can convert the non-unity feedback system to the unity feedback system by just manipulating the block diagram. Okay, so this is important point, and once I'll solve the question you'll get to know more about this. So one more thing I want to discuss over here is the order of the system and type of the system. So order is defined as the total number of poles in closed loop transfer function. This CLTF is nothing but the closed loop transfer function, and the type of the system is the open loop poles at origin. Okay, so this can be determined from the OLTF, and this is determined from the CLTF. So order and type. Here is one relationship between the order and type of the system. So type is greater than equals to 0, less than equals to order. So type is always less than or equals to the order of the system. Okay, and one more important thing I want to discuss over here is steady state. Like steady state error depends on the system parameter, and yeah, on the type of the system, as it is independent of the order of the system. It does not depend on the order of the system. Okay, yeah. Here is one table, and I suggest you to just remember this particular table. If you remember this table, you can save time while solving the questions. So here is the steady state error, here is the type of the system, and here is the input provided to the system. These are all inputs. Okay, so when you provide the step input for the type 0 system, here is the steady state error value. And for the type 1 system, when you provide the ramp input, here is the steady state error value. And for the type 2 system, when you provide a parabolic input, here is the value of the steady state error. So as you all can see, the lower triangular matrix is constituting like it consists of zeros, and for the upper triangular matrix they are from the infinite. Okay, in this way you can remember this. And yeah, so the another important point over here, like I have used kp, kv and ka. So kp is nothing but limit as tending to 0 open loop transfer function, and this kp is known as the positional error constant. Here kv is limit as tending to 0 s into OLTF. Here kv is the velocity error constant. Again, k is limit as tending to 0 as square into OLTF. Here it is an acceleration error constant. So this table and this particular box, they both are important. Okay, you must know these two, and by these two you can easily calculate the steady state error. Yeah, here is one important statement I have given. Like when the type of the system increases, the order increases, the number of oscillation increases, and stability decreases. As you all know, when there is more number of oscillation, there will be a system with less stable. Okay, like see, you can see over yeah, this analysis is very important, and you must remember this. Okay, yeah, you can see over here like the steady state error for type 0 system for step input is 1 upon a upon 1 plus kp, which is finite, and but for the ramp input it is reaching to the infinite. Okay, for the type 1, for the ramp input it is some finite value, but for the parabolic input it is going infinite. Okay, yeah. So the next point, yeah, here are the few examples. So by that, it will be very clear for you. Okay. So the first example I have given over here, you can see the block diagram. Here, this is not a unity feedback system. As you can read over here, the block diagram, the given system is non-unity feedback. So you have to convert it into the unity feedback system. So here I have applied one trick to convert it into the unity feedback system. So when we consider this entire block, so yeah, our like this, it will become over here. This is 1, this is g. Okay, so g can be calculated from here. So g is nothing but what you can say 1 by s divided by 1 plus 1 by s into this is 2 minus 1. So this g is nothing but 1 upon s plus 1. Okay, so g is nothing but g equals to 1 divided by s plus 1. Okay, so with this you can calculate the transfer function equals to 1 by s plus 1 divided by 1 plus 1 by s plus 1 into 1, like this. Okay, so this is basically how to convert the non-unity feedback system into the unity feedback system. Okay, so for the steady state error, like if you want to calculate the steady state error equals to limit as tending to 0. For the step input we want to calculate, so s into r of s is nothing but 1 by s divided by 1 plus g of s, which is equals to 1 by s plus 1, and h of s is nothing but the unity feedback system. Okay, so this is the way you can calculate the steady state error, so which is coming as e steady state error is equals to limit as tending to 0, this s will get cancels, and yeah, this will be s plus 1 divided by uh, s plus 1 plus 1, so this is nothing but s plus 1 divided by, no, you can just directly put the limit, so it is nothing but 0 and 0, so it is coming as 1 by 2. Okay, so this is the value of the steady state error which you will get from this particular uh, transfer function. Okay, yeah. So the next example is example number 2 over here. Yeah, so its transfer function is given to us. Whenever they say transfer function, it is nothing but closed loop transfer function. Okay, so when CLTF is given, how will you find the open loop transfer function? So when CLTF is given to you, for example, here the transfer function is 1 by s cube plus 3s square plus 4s plus 1. So for this, the open loop transfer function is given by this quantity, whatever is present over here, that you have to subtract over here. So this is nothing but 1 divided by s cube plus 3s square plus 4s. This is the open loop transfer function. So when you observe the open loop transfer function, it is the type 1 system. So type 1. So number of open loop poles at origin equals to 1. Okay. Yeah. So since it is the type 1 system, so for the step input, E steady state error for step input equals to 0, and E steady state error for the parabolic input equals to infinite. Okay, so we just have to calculate the steady state error for ramp input, and from the table itself it is equals to E steady state error is equals to A upon kV. Okay, here I'm assuming this A equals to 1. Okay, so when you calculate kV, so kV is nothing but limit as tending to 0 s into open loop transfer function. This is the open loop transfer function over here. Okay, so when you put the open loop transfer function, it is nothing but 1 divided by s into s square plus 3s plus 4. So this s and s will get cancelled, and when you put the limit, the kV value is equals to 1 by 4. Okay, so your steady state error will become 1 upon kV, which is equals to 4. So this is the answer for this given question. Okay, this much easy it is to calculate the steady state error. Okay, yeah. For the next question, we have find the steady state error for the unity feedback control system having the transfer function g of s, which is equals to 100 divided by s plus 2, and input signal is r of t, which is equals to 5 plus 2t. So as this given is this input signal is given in the time domain, so r of s equals to 5 by s plus 2 by s square. Okay, you all know that, like when you convert this time domain to the s domain, we just by taking the Laplace transform, you can just convert it into r of s. Okay, so this is nothing but you can just make it as a square 5s plus 2. Okay, as we all know, the steady state equals to limit s tending to 0 s into r of s divided by 1 plus g of s into h of s. As it is given unity feedback, so it is equals to 1. So steady state error equals to limit s tending to 0 s into r of s is nothing but 5s plus 2 divided by s square divided by 1 plus g of s is nothing but, it is given in the question, it is equals to 100 divided by s plus 2. So when you solve it, it is equals to limit s tending to 0. This 1s will get cancelled over here. So it is equals to 5s plus 2 divided by s into s plus 2 plus 100 divided by s into s plus 2. So this s will also get cancelled. So over here I'm writing, so this is equals to limit s tending to 0. This will equals to 5s plus 2 into s plus 2 divided by s into s plus 2 plus 100. So when you substitute the limit, so yeah, from the by substituting the limit you will get 2 into 2 4 divided by 100. So it is equals to 1 divided by 25, which is equals to 0.04. So this is nothing but our steady state error for this particular question. Okay, so I hope these examples are very much clear to you. So thank you, have a good day.